So, they have a small heat sink, and we have a, there is a front wall, then we have a, what do you call it, trays, and we have all the, this is the enclosed cabinet inside. So, how things are attached to the thing. So, we have a hinge which helps in probably lifting the this thing. This door can be lifted, and then this can be lifted out, and we can see how things work. And on the upper tray you have heat what do you call generating components, and the lower tray we have other things mounted here. And using this they have tried to make, you see here everywhere neat sections are there. So, each point nodes are kept here, saying there is a 19 starting at this, all these points, total 26 nodes have been evaluated. All that is possible to construct an equivalent electroc analog for a 3-dimensional heat transfer if the problem can be simplified into 2 dimensions. Can we read it again, read it again? This is, remember, these are all early analysis, way back 45 years back, or even it may have been 50 years back when they started the analysis. It was not easy. Right now full 3-dimensional QFT type of things are possible to be solved perfectly. Next I have, maybe in the next slot I will show you things from another what do you call commercial company. So, they said heat gradient in the direction perpendicular to the plane is assumed to be 0. It is not a very good approximation. Oh, sorry. Just same thing which I had read out. Divide into 3 sections, and a number of nodal points are embedded accordingly. It is a temperature at this point that we wish to compute for a given amount of heat generated inside, done by computing the nodal voltages of the equivalent electrical circuit. Number of extra nodes of special significance are incorporated in the model. So, I will now try to jump and I will try to come back. Resistors ending at ground in this circuit represent radiation and convection from the cabinet walls to ambient, really to end on constant voltage sources of a value corresponding to the ambient temperature. The computation temperature above ambient will give us complete information about the thermal properties of the cabinet, constant voltage are justifiably short circuit or not. Here we end up with a very peculiar this thing. Sir, if you can kindly show me this. We have some source inside mounted here, and then we have a heat sink. Unless this spreader is above the ambient temperature, it cannot transfer any heat to the ambient, and unless this spreader is much lower voltage than this, it cannot absorb heat from there. So, the optimum temperature of this what do you call convector is also very critical. This is where now we need to do a bit of optimization. If you make it very big and all, that is only waste of material and increasing weight and cost, whole thing. If you make it very small, while this temperature is high and it can transfer effectively to the ambient, it does not, the temperature differential here for heat transfer by conduction reduces. So, coming back to this again, you see here, next one you will see the computation of the temperature rise above ambient will give us complete information about thermal properties of the cabinet. So, this constant voltage is justifiably right now short circuited. So, assuming this is not what you call, while it is not impossible, maybe I should make it a little smaller. I am not able to what do you call heat generating components are situated in the heat sink and in the lower compartment. The resistors R1 to R8 represent the heat conduction of the interior cabinet trays, R18 to the heat conduction of the cabinet proper itself. Conduction in the vertical direction of the front and rear cabinets is shown by and so on. Connection between the cabinet and the heat sink and between the cabinet and the lower drawer accounted by resistors. Describe the thermal baths between the front wall and the this thing. Now coming here, this is what he was talking about. So I will give you a link. I suggest you take a printout and try to read carefully. Equivalent electrical circuit. You see here, no, this is what he was talking. What is shown as ground are the things which are transferred to the ambient. So if you remember in the old thing, no, we had 26 and then we had 1, and then all these things, no, represent various types of what do you call conductions and so on. So we have here, no, large number of sources which generate heat and they are transferred to the heat sink at the bottom. So you have the capacitance and then you have various things which are related to this here, and from here onwards, they are all much smaller, and then there is no heat generation. You have seen this, no, these are all the heat generators inside the cabinet. Having gone through this, resistors at ground describe the combined effects of radiation and convection of the cabinet. Transient heat properties are accounted for by the capacitors, are computed using the equations described previously, and for ease of recalculation written into a computer program. The effects of changing material surface finish, cabinet mounting on the equivalent circuit components can then very easily be derived, means you can check, keep checking the variables. Values of the current generators simulating the heat generation inside the cabinet depend on the power losses in the transmitter and the output amplifier. These calculations are based upon estimated transmitter and output amplifier efficiencies. This is what I had mentioned to you in passing in my vocal this thing. Every circuit has a inefficiency. So in my case, I will try to see, now just see here, it says it has a voltage of 160 amperes and then I am sorry, current of 160 amperes and a voltage of 36 volts. If I round it off, let us say 30 volts at about 100 amps, so this is supposed to be a 3 kilowatt nominal, actually if you multiply 160 into 36, almost a 5 kilowatt device. So we had actually used it, something about 3 kilowatt. The thing is, what is the efficiency of it at all conditions, typically part load efficiencies. We are still trying to see whether during part loads, which is the most efficient configuration, electrical configuration, by which not long ago we are worried about power and we are worried overall about the other effects including current, voltage and all. Right now a lot depends on not just power but the total energy efficiency of it. So we are trying to compute it, hence the device here. So I will notice here the power losses in the transmitter section and the LF audio what you call output amplifier. These calculations are based upon transmitter and output amplifier inefficiencies. So that is where actually the problem starts, and the reason also why, if you take a switched mode power supply. These days in smaller and smaller packages we get specifications like 19 volts and 10 amps and so on like that, because specification also has changed a little. Maybe the analogy, me being a mechanical engineer, I can draw the analogy to the engines that are mounted in cars and the engines that are mounted in motorbikes. So, if you take a 600 cc motorbike and you see the BHP, it shows ridiculous figures. Same 600 cc in a car, which is typically what the Kai Jidoshi small car thing we have, the power output is small. So, it is partly due to convenient new shampoo and snake oil type of advertisement, but everything is measurable, the conditions are correct, it is correct. Smaller engines mounted on open chassis in motorbikes seem to be producing a lot more power than the other things. Typically 1 liter engine can probably generate about 75 bhp, and the same 1 liter engine on a motorbike, you check it up, I will not deliver the punchline. If you read along with me on this, the heat distribution during transients is important, as well be the case when the transmitter is activated only intermittently, normal mode of operation. Then a transient analysis of the equivalent network with capacitors is called for. The ECAP program admirably suited for solving. Results of the ECAP DC analysis of the equivalent network are shown. Refer to worst case where both transmitter and the receiver are in constant operation. Probably have a look at it. Temperature difference in the upper tray with the distance from the rear wall, and then rear wall of the cabinet, the various types of temperature differences have been plotted here. So, in the succeeding write up, seen that these dots seem to be nicely very close to the computed things. So, in this case, once upon a time it was difficult. When our chance came, when we wanted to do this analysis, what we did is we made huge printed circuit boards, typically which are 10 inches high, that is approximately 25 centimeters, and between 30 to 35 inches deep, and made it into a grid mounted standoffs, that is a small brass, copper pins, and resistors. Physically we knew the profile of each of the printed circuit boards where hot things are there. We simulated them by mounting resistors across each of these things, and the whole thing had a bus structure here. You had a positive voltage at one end and then a negative voltage, and the whole thing was put into the racks. Now, this is where we ended up with a beautiful thing. Then we had a probe at the back, the whole rack was covered. There were small openings in which probes could be inserted. So, some of you may remember old transistors 33, I do not remember the number now. It is a small compensated absolute temperature sensor which was inserted, the depth could be controlled and vertically you could move it a little with the back closed. So, we use this temperature sensors and physically scanned a cabinet which had some 14 PCBs horizontally and total 6 what do you call rows of it. So, we had columns and rows and the depth full 3D and plotted everything manually. That was the only way things could be done way back when we started. And while these people have only few of the points here, we had a full grid of all the 3-dimensional thing which we could do. That is one of the reasons why I have been asked to talk about this. Now, when we go to the next page, you have seen this here. To confirm the theoretical analysis, temperature rise was measured in number of points in the experimental cabinet existing at the time of study. The power losses were simulated using epoxy embedded resistors glued to the chassis at the approximate positions of the future heat generators. This was the way everybody was working at that time. Can you see it? The only way is you take a small area, and in the case we were it was possible, we are trying to simulate point things by keeping the what do you call that resistor directly into another small case. And if we knew that is going to be a small heat generating device, we used to take a 30 mm by 30 mm plate and then use resistors which can be directly bolted onto it. You would have seen the power resistors where, and then we were giving separate voltages to them to ensure that in a small area of 30 mm by 30 mm, if something is likely to dissipate 1.5 watts, that is will be very different from something which is heating up the air in general, which is exactly the same thing. Glued to the chassis at the same positions of the future heat generators, transistor, the transmitter and the power amplifiers, greatest deviation between computed measured temperatures was only about 3 degrees centigrade. Then it comes to the circuit which I had shown earlier, was put through the CCAP program and then impulse was applied through the current generators. ECAP program prints out voltages at all nodes using transient, shows the heat rise of just 2 of the nodes, warmest and the coolest. Again, measurements on the experimental cabinet were performed with the result indicated in the figure. So, nodes 9 and 26 for a constant excitation. You see here one very important thing. With the time, there is a stabilization that is required. In our own analysis, what we found out is that when we excited the racks and kept, and things were okay because we wanted to use a natural ambience, which fortunately for us in the place where we live in Bangalore, and inside this beautiful wooded almost like a park, things were cool. But the thing is, at the peak of summer, maybe temperatures would come to maybe 32 degrees, and the first sign of any clouds, any passing cloud also, all that whole cabinet will become cooled down significantly, as order of at one point maybe 7 or 8 degrees things have come down, which is very good. And at that point we try to add loose circulating fans at the bottom. Unlike these fans, which they are all made such that you have seen that maximum amount of area is covered. But if you see a propeller of a normal turboprop airplane, very little area is covered by the propeller, because that's detrimental to other things. Fans which look a little like the turboprop things but large diameter, all of them, the probably smallest was about 35 diameter. 30 is so much and 35 is so much, and 2 in each of the thing at the bottom running at a derated speed. And again you would have noticed here important thing, if you were to mount something as an exhaust fan or something sucking at the bottom, it will see the high temperature produced here, but if you have to use it as a blower from the bottom, you have the advantage that the fan itself will see lower temperatures. Having done that, we have found out that it is very much possible for us, in spite of it, the top row were getting hot. So, in between one more shelf was created, external cool air was fed through it from the bottom. So, if you see, if this was the rack, cool air, hot air exited, then we decided to put a horizontal input separately, and cool air again goes up, and this hot air which goes here was taken out like this. So, which will come to the next level of system design. Do we fit air conditioning to the whole room? I will see if I get a chance to take a picture of the air conditioning what we have. All air conditioning seems to be very effective in freezing the operators and students inside the room, while the equipment randomly keeps getting hot. To avoid all this, separately ducting was suggested, saying you provide the ducts where the input is there, and most important, give filtered air. Anywhere you have any of this forced cooling, we have the issue of these fans work quite a lot like your vacuum cleaners. I do not know whether you use the word Hoover and now, or Dyson or any of the trade names, but they are vacuum cleaners, and vacuum cleaners, they provide more suction than we ever need. So, you see here that transient analysis was okay. The circuit of figure was then subjected to transient analysis. Close and measurements on the experimental cabinet were performed with the results indicated. A transient analysis were performed with the transmitted excite intermittently following the pattern here. This is typically what comes here. Long ago, I think when the second lecture I had mentioned to you, everything, very rarely anything runs continuously, including your own power supplies. You have a duty cycle. So, this typically represents the duty cycle of the cycle, I mean of any of the items. So, steady state temperature rise after infinite time is approximately 12 degrees centigrade for the above excitation, compared with 33 for the worst case with the constant transmitter. You have seen that, no? This factor seems to be so much, 3 times. To give some indication of the expense of running, they have given some figures. I will not understand what this nice sitting thing is. It is probably a pound sterling. It is 0.75. Transient analysis is 30 pounds, and something else is about 33 pounds. I do not know the duration or anything. It is obviously it is expensive. At that time, probably salaries were much less. When in designing cabinets, it is possible to reduce the true 3-dimensional heat transfer to a simpler problem in 2 dimensions. An equivalent electrical network may be postulated. In a fairly straightforward manner, the components in this equivalent circuit are best calculated by a computer program, whereby the influence of cabinet dimensions, material thickness, etc. can be investigated. Computation of the transient temperature rise can then be performed. Findings reported in this paper indicate that acceptable accuracy. Then the next page is probably full of all the acknowledgements. I am very happy. I also acknowledge all these this thing, and probably physical design of electronic systems is the same book which we also referred when we were doing these things. allow me to close this point and try to go to a nice what do you call these days. This thing can be easily be evaluated by the modern programs we have. I have seen this, no, all these resistances and all, while that was more a PhD thing. Coming back to, we have a package level analysis, then we have circuit board level, then we have frame or system level design, okay. And this comes to, we have all these beautiful colored pictures only. With due respect for the people who have made it, I have left all these things saying, you know, degree controls cooling, saying it is nice to think that, you know, things are so obvious, except when you are using a IR camera, these are still what you call visualizations that is created by very intelligent what do you call people. So, for even, you know, all these type of you know, what do you call multiple lead packages and all that, and consideration of a board, this is what I was talking to you. It is nice to think, saying this is how it is. It is intuitive. At the bottom, no, they have got what do you call 90 degrees, I am sorry, at the top they have 90 degrees and the bottom about 60 degrees, and I know how the this whole what do you call temperature profile can be created. So, I leave it at that, because me being from the academic field, I take all these what do you call presentations a little with this thing, saying I do not agree that they are bad, but conditions apply, and a little bit of creative visualization. I am sure your TV is bombarded with how to make your life better, with left side bottom corner a small flash saying creative visualization. I will take leave at this point and then try to continue in the next lecture. So, thank you for patiently going through this. One more time allow me to acknowledge, saying this is being meant as a educational exercise. I fully acknowledge the original authors from whose work I have taken, and to make it authentic, I have presented the original work instead of trying to add my own what do you call coloration to that, because things will get lost in translation, and worst is transliteration. So, my stock example is the what do you call color of the heat sink, and coming all the way to contact resistance and all the way to the thermal imaging which they show there. So, believe in what you do, you verify yourself. So, thank you. Go back to each of my lectures, go through it, and be patient until we come to the end of the course. So, thank you.